Hello and welcome to lesson 2 of the topic on calculus. We will start with differentiation from first principle. Basically, the first ideas, what differentiation entails, all right? So let's discuss the first principle, but before we go there, I want to take you to a simulation and I just want you to take a look at this. Before we begin, right, what you see is a graph that I've done using Geogebra graphing package. What I would like you to do now is to take a few seconds, let's say 10 seconds, and perhaps write on a piece of paper, just describe what you think you see on the graph. Okay, so 10 seconds. Right. I'm hoping that at least some of you have said that you see a straight line. You probably see the point marked on the straight line with coordinates 1, 2. Okay? Well, you may be right, but again, you might be wrong. And let's see just how wrong you might be. Well, if I zoom into this point, I'm going to try and zoom into that point. We notice that it's not exactly a point. As a matter of fact, I see at least 5 points. So what appeared to have been a single point is in fact 5 different points. Now when we started, we said that one of the things you need to be able to do, to be able to understand differentiation or calculus, is to be able to determine the gradient of a straight line. So assuming this is a straight line, then we could pick 2 points and use them to determine the gradient of the line. And how do we do that? I know the coordinates of one point. I could determine the coordinates of the next point there. So if I show the label for that point, here are the coordinates. Now the gradient of the line is given, let me write this here. So the gradient of this line is given by m is change in y over change in x. We write that as delta y over delta x. So I could say y2 minus y1 over x2 minus x1. Okay, now if I look at this, y2 is 2.404 and this is 2, so the difference in that y2 minus y1 has to be 0.00004 divided by change in y would be change in x, that is, would be x2, which is this one here, divide by x1, which is just 1. And if we subtract that, we can see that the difference is 0.00002. If we divide these two, we get that the gradient is 2. I could find that gradient by using another point or 2 other points. Since this is a straight line, the gradient that I get should be 2, whether I'm taking this point and that point, or if I pick a completely different point like this and that. So if I pick this point, for example, I'm going to use 1, 2 because it doesn't have decimals on it. So if I remove this, or let me just put this here first. So if I pick these coordinate points, show the label for this point, well, now this point has coordinates, how many zeros? 4 zeros and 8, and this is 4 zeros and 4. So again, the difference there would be 0.04, okay? Picking these 2 points instead of this point and this point. So 2.4 zeros and 8 there, and 2.4 zeros and 4 gives me the same thing. And 1.404 and 1.402 gives me the same thing, 0.402. And therefore, when I determine the gradient, I'm going to get the exact same thing. And that is expected because this line is straight. So as long as we have a straight line, the gradient would be the same, irrespective of which points you select. So I'm going to put the coordinates of this point, and I suggest that you try and look for the gradient using 1, 2, this point here, and the next point. So just pause the video and try to confirm that point, let's call this point A, and let's call this point here C, And I would like you to try and find the gradient and confirm that you find the same gradient of 2, okay? All right, let's continue on. Right, let me now remove the coordinates of the point and investigate this straight line, so-called straight line further. I'll remove the coordinates of that point as well as this one. So we are left with one single coordinate point, right? This time, instead of zooming in, I want to zoom out. So if I zoom out, here are my points just like before. Let me bring it closer to the center. As I zoom out, I get my single point. Remember that that single point is in fact 5 different points on the same spot, or appearing to be on the same spot. So a single point like this could actually be representing more than one point. Other than that, a single point might actually represent a line, as we have seen earlier, all right? But if I continue to zoom out, you can see that my single point there, I'm even going to make it smaller so that we can continue to zoom out more. I'm going to reduce the size of that circle, okay? There we go. And I'm just going to, so that's that circle that we had. So if I continue zooming out, you notice that the circle, which as you can see, this is a straight line, but if I continue zooming out, the circle turns out to be just another point. In addition, it should also be abundantly clear now that what appears to be a circle is a point, and what appeared to have been a straight line wasn't a straight line at all. In fact, it was a curved line. In this case, this is a cubic function. All right? There are questions that we can ask ourselves on the basis of what we've just observed, right? One of which is, how many points can we form inside a point? Well, this is a point, but we just realized that it wasn't a point at all. It was a circle, okay? It was a circle, which appears to be straight, with a line, a straight line inside it, okay? And another point inside the straight line. And even that point was in fact made up of more than one point. So how many points can we actually create on this line, the line that happens to be inside a point? How many points can we create inside a point? All right, so these are some questions that we ask ourselves in TOK, and forms a very good basis for beginning the discussion on differentiation. Now let's talk about the first principle of differentiation, okay? The first principle is really just about understanding what it means to differentiate, or what it means to find the derivative of a function. So what does it mean to differentiate a function, okay? In order to understand this, we've looked at that simulation. So from that simulation, there are some questions that we may want to ask ourselves, all right? And in IB, we think of this as falling under theory of knowledge. How many points can we arrange in a straight line inside another point? All right, how many points can we form in a straight line inside another point? What kind of answer might you give to this kind of question? All right, is there a limit to the number of points you could put inside a point? All right, well, I am trying to convince you that a point really contains a short straight line. So every point drawn on a line will is made up of a straight line. So a point such as that one, if we were to zoom in, that point we will find is in fact just a straight line. So if I zoom in like that and we check, we'll find that there is a straight line there that is lying in that orientation. So that's the orientation of this line, okay? So as a matter of fact, we can plot infinitely many such points along a curve. So this is just one of them, but I could have so many of them along the line like that. All right? Each of those points is actually a straight line just like this. Okay? The only difference is that they face different directions, so that at a point like here, the line might be facing a completely different direction compared to this. So at that point, the line has got a negative gradient. At this point, the line has a positive gradient, but at that point, the line that is contained in that point has a gradient that is negative. At this point, that line will be horizontal. So the key is that every point is made up of a short straight line. Okay? So a curved line such as this one can be viewed as a chain of infinitely many points, with each of these points being a short straight line. And I might go further and answer this question and say that inside that point, which contains a line, I could add infinitely many more points. So there are, in fact, infinitely many points that could be arranged in a straight line inside a point. All right, hoping that is you found that interesting or something to think about. Okay, and now let's begin differentiation from first principle. Let's consider such a point P on the graph of a function y is f of x. This function could be anything. It doesn't have to be quadratic. It could be any of the functions. So let's take a look at such a point that we've discussed. All right, let the point be P on the curve y is f of x. Line y is f of x could be any line really. So there's my point P. Remember, in there is a straight line. So the function represented by this curve, f of x, could be any type of function. All right, it doesn't have to be, all right. So first of all, a point P, which is on our line y is f of x, has coordinates x, which we have indicated there, and y value. So instead of y, I'm going to choose to write f of x. Okay? So if that's the line and this is the function, please remember that this function could be any type of function. Really, we don't need even to know how the graph looks like. We just need to know that there is some kind of a curve. You can draw it in any way. You don't need to know what the function looks like when we sketch it. So the function can be anything. All right, it could be a power function, could be a polynomial where k is an integer, or it could be a power function where k is a decimal number. All right, it could be a trigonometric function, it could be a logarithmic function, it could be an exponential function, or even a radical function. All right, so this is called the radical sign, so the square root, the cube root, and so on. Could be any of those functions, it doesn't really matter. Then a point on such a line having coordinates x and f of x is what we are showing here. If I zoom into that point, what we are saying, so what you're seeing here as a circle is actually a point. We have just zoomed in it, all right? As we zoom in, we are supposed to get closer. The line that we get here tends to be a straight line. So I can zoom in and then take a smaller circle and so on, so that my point is as small as possible. So knowing that this line inside here is made up of points, I might just pick another point at the center of our point P. So let's pick a point there and call it A. I can pick a second point there and call it B. All right. Now, if my point P is tiny enough, then the radius of that point P is very, very small. The radius, that means the distance from here to there. The distance from A to B is very, very tiny. If I consider a point that is very, very small. All right. In that case, I can draw a line from point B, and this must be a very, very small distance since my circle is tiny. Let that distance be delta x. Delta to mean a small change in x. If that's the case, then the x coordinate of point B must be x plus delta x. So suppose delta x is, let's suppose that delta x is 0.0001, and suppose that the value of x is maybe 2, then we are saying that the value here is going to be 2 plus 0.0001, like that. And so the coordinates of this point is going to be x plus that little change, delta x. So we're going to have the x coordinate of point B as x plus delta x. And if that's the case, we know if this is x, then the y value is f of this x. All right? So if point B has coordinates x plus delta x, then the y coordinate is going to be f of x plus delta x. In other words, y2 is going to be f of x plus delta x. So this value here is in fact delta x. Okay, my bad. We can use h, but if I use h here, then I need to use h here. But this is intended to be delta x here. This is delta x. Okay, so for a value of x, the value of y is f of x, and therefore for a value of x plus delta x, the value of y is going to be f of this. Okay, and using that, we know that the change here, this distance here, the increase when we move from point A to point B, the rise is going to be a delta y, change in the y direction, and on this side we're going to have change in x direction, and so the gradient of our line can be found using the idea of change in y over change in x, or if you like, rise over run. So if we say the gradient is rise over run, then the gradient of point P, the gradient of point P. So we can actually find the gradient of a point because a point is a line, according to our discussion from before. So the gradient of this line, and remember the gradient from A to B is the same as from B to another point here, C. I don't know if I put it there, yes, because remember this is almost a straight line, okay? But this is an approximation because my point is very big, so you can see this is actually a curve. The reality is that as I make my point P smaller and smaller, the result, line CAB, becomes a straight line and the gradient becomes better. We can talk of gradient of line CAB provided point P is very, very, very tiny. Okay? So as we make point P smaller and smaller, as we make the radius of this dotted circle representing point P, as we make the radius smaller and smaller, the result is a straighter and straighter line, so that when we find the gradient, is a better approximation of the gradient than trying to look for the gradient of CAB. And therefore, when I look for the gradient of CAB or line AB, it is an approximation, and we write the gradient is the change in y over the change in x, which is y2 minus y1 over x2 minus x1. Which from here we can see is this is my y2 and this is my y1 and this is my x2 and this here is my x1. So if we write that down there, we get y2 minus y1 over x2, this whole thing here, x plus delta x is my equivalent of x2, subtract x. All right, if I simplify that, what do I get? You can see that x here is going to cancel with that x there, and I'm only left with delta x in the denominator. So the approximated gradient of point P, another point P is the dotted circle, so the approximate gradient of that point expressed as delta y over delta x at point P is approximately given by that expression there. Now this might not appear to make sense now because we are talking in general, but we will soon see how this becomes useful, okay? The derivative at point P. So we've looked at the approximate gradient at point P, and we've seen that it is given by that. We call that an approximate gradient. Why? Because as you can see, CAB is not exactly a straight line. So we cannot talk of the gradient of a curved line. We can only talk of the gradient of a straight line. Okay? So if we wanted to find the true gradient at point P, we need to make that circle smaller and smaller. The smaller that circle becomes, the better is the line CAB. And if that's the case, then if we are making that smaller and smaller, then delta x is becoming smaller and smaller. All right? So let's just see if we can find the gradient when the circle is very, very, very tiny, so that delta x here is tending towards 0, it's becoming smaller and smaller, because it is when delta x is becoming smaller that this tends to be a straight line. Okay? So if we can find the gradient when this eventually becomes a straight line, that gradient that we find is going to be referred to as the derivative of this function f of x at that point P. Okay? So the derivative of f of x, so the derivative of this curve at point P refers to the gradient of point P as the circle representing point P gets smaller and smaller. All right? When line CAB becomes a straight line, then the gradient we get becomes the true gradient, and that true gradient will be referred to as the derivative of this function, but at point P. The derivative of the function will be different at different points because, as you saw earlier, as we saw this earlier, we noticed that every point on the curve, let me go back and show this again, we saw that every point on the curve will have this line facing different directions. Okay, so the gradient or the slope will be different at different points, and therefore the derivative of the same curve, which is the slope, will be different at different points. So we can only talk about the slope at some point P, which is what we refer to as the derivative. All right? So therefore, we conclude that the derivative of f of x at point P is the true gradient of at point P, which we can only get as point P gets smaller and smaller, or better still, as delta x here, the radius that we had there, as that radius gets smaller and smaller, that becomes a straight line, and therefore the gradient becomes the true gradient. And the true gradient is what we refer to as the derivative of the function at that point P. I'm hoping that this is making sense. Okay, so let's go and hopefully we can look at an example before we stop the class. So we can say the gradient, we've already talked about this. So the approximated gradient is that, given by that. And so the true gradient, which is called the derivative of the function at point P, will be given by, so we take the approximation, and what we want to do is we want to make delta x very, very, very tiny. So as we make delta x tinier and tinier, we arrive at the true gradient. Let's reason with that briefly. Okay? We've already reasoned, but let's just line it up now nicely. So we reason that to find the true gradient at point P, line CAB here needs to be very, very straight. We want it to be straight. And the only way to make it straight is to make this circle here, which is our point P, we want to make it smaller and smaller. And you can see that as I make it smaller, right, as I make it smaller and smaller, already you can see I've made it a bit smaller. This is turning a bit more straight. Okay, delta x, which is this distance between these two lines here, is getting smaller and smaller. Let me make it even smaller. All right, you can see that as it gets smaller, the line we have inside our point becomes more straight, but delta x has gotten even smaller. So we are saying that as delta x gets smaller and smaller, what we end up with here is going to be the true gradient. Okay, so this is going to be the real thing. It's no longer an approximation. It becomes the true gradient, which we shall refer to as the derivative of the function at point P. All right, the true gradient, which we no longer write like this, we replace those triangles with letter D. All right, that is the true gradient, is the limit. We say that the true gradient is the value of the gradient that we get as delta x tends to 0. We say that the true gradient is the limit of our approximation as delta x approaches 0. So our approximation tends to become the real thing, provided we make delta x as tiny as possible. All right? In mathematical notation, we write that the true gradient dy by dx is the limit. That's why we needed to understand a bit of limits at the introduction. So we write that the derivative of f of x at point P is the limit, okay? So dy by dx, the true gradient, is the limit as x tends to 0, as this distance here, as delta x tends to 0, of the approximation delta y over delta x, okay? We write dy by dx, remember delta x over delta y was expressed like this, so the true gradient is the limit as delta x tends to 0 of this expression here, all right? And that is an important expression. That's really it. If we can do that with different functions, then we are actually differentiating. In the next lesson, we'll talk about how to use this relationship to find some specific derivatives for certain functions, okay? Thank you very much. I hope you've understood this, but we will be looking at a real application of this relation that we've come up with. This relation is really the principle behind differentiation, all right? Differentiation from first principles. When we hear we are finding the derivative from first principle, effectively this is what we are doing. We are looking for the real gradient which occurs as we make the circle or the point smaller and smaller, so delta x is tending to 0, so that we end up with a straight line at point P, all right? Thank you very much. I'll see you in that next video.